In the third part, we will continue to look at what the science says. So what does the good science say? The media would have you believe that climate scientists are divided into two camps, the consensus and the deniers. Firstly, science is not done by consensus. It develops through a continual challenging of conventional beliefs. Secondly, note the emotive use of the word denier, placing those who question the consensus in the same category as Holocaust deniers. Actually, there is a great level of agreement among climate scientists. Where they differ is in degree. For example, MIT Professor Emeritus Richard Lindzen agrees that fossil fuel emissions are warming the atmosphere, and yet Wikipedia lists him as one who disagrees with the scientific consensus. Let us look into the main areas of agreement and contention. Why does CO2 trap heat and, for example, oxygen does not? The carbon dioxide molecule consists of one carbon and two oxygen atoms, while the oxygen molecule consists of just two oxygen atoms. Incoming infrared radiation, in other words heat, causes the CO2 molecule to vibrate, thus converting radiation energy to kinetic energy. The heat is therefore trapped momentarily before being re-emitted, perhaps to the next molecule. Oxygen molecules can also vibrate, but being smaller are not activated by infrared wavelength. Water vapor, the largest greenhouse gas by far, also traps heat in a similar way, as does methane, but they operate at slightly different wavelengths within the infrared spectrum. So the important question is, how sensitive is the temperature to an increase in CO2? This is referred to as CO2 forcing. It is customary to consider the effect of doubling the CO2 content. Scientists agree on a figure of approximately 1 degree centigrade of warming per doubling of CO2, so there is agreement so far. However, the increased heat in the atmosphere has a knock-on effect on the land and the ocean. We can imagine that plants grow faster in a warmer climate, thus drawing CO2 out of the atmosphere. On the other hand, a warmer ocean would release carbon dioxide, thus adding to atmospheric CO2. Again, a warmer ocean may give rise to more clouds, giving rise to a greater reflection of the sun's heat from low-altitude clouds, or the trapping of more heat by high-altitude clouds. These are called feedback factors, where those which increase temperature are called positive feedbacks, and those which decrease temperature are called negative feedbacks. One can imagine innumerable factors which either increase or decrease temperatures. Clearly, this is a very complex problem. Scientists estimate the effect of feedbacks in watts per square meter of the Earth's surface. The effect of the total of feedback factors is then applied to a formula. Increase in temperature for a doubling of CO2 equals 1 degree centigrade divided by 1 minus F, where F is the sum of feedback factors. This formula is a simplified version of more complex differential equations, but is useful for illustration. Note that if F is 0, then the increase in temperature for a doubling of CO2 remains 1 degree. On the other hand, if F is 1, then the increase in temperature is infinite. The formula mentioned describes a rectangular hyperbola. We see that if F equals 0, then the effect of doubling CO2 remains at 1 degree. As F increases, then temperature increases more and more rapidly, becoming infinite at F equals 1. The 2013 IPCC estimates are those in the middle, showing temperature increases of between 1.5 and 4.5 degrees. Alarmists would believe even higher values, whereas the so-called skeptics suggest lower values. This is the nub of the CO2 warming debate. The rest is just noise. We have already seen how satellite temperatures contradicted climate models. Now we consider the link between temperatures and atmospheric carbon dioxide. There are several land-based temperature records, but to the extent that we have faith in the temperature records, we will consider the National Climatic Data Center NCDC from NOAA. This chart shows the increasing CO2 levels in red and temperatures in blue. What is interesting is the strong correlation between temperature and CO2 between 1978 and 2004. However, the correlation is weak after that and negative before 1978. Why did temperatures actually decline between 1958 and 1978 while CO2 was rising? Also, why did temperatures not continue to rise steeply between 2004 and the present? Could it be that the years 1978 to 2004 merely correlated by chance? The explanation for the years when temperatures did not correlate could be ascribed to more powerful natural climatic factors. In which case, could the whole period not be ascribed to natural climatic factors? We examine ice core results from the British Antarctic Survey. I quote, "By measuring the ratios of different water isotopes in polar ice cores, we can determine how temperature in Antarctica and Greenland has changed in the past. The oldest ice core we have was drilled by the European Project for Ice Coring in Antarctica, EPICA, from Dome C on the Antarctic Plateau. It extends back 800,000 years and shows a succession of long cold glacial periods, interspersed roughly every 100,000 years by warm interglacial periods, of which the last 11,000 years is the most recent." End quote. There are some takeaways from this data. 1. Carbon dioxide lags temperature, so carbon dioxide is the product of warming rather than the cause. 2. We are now at the start of an interglacial period, so if the process repeats, we are beginning a long slide towards the next ice age in about 90,000 years. 3. Carbon dioxide at 400 parts per million now exceeds the maximum level over the last 800,000 years. In fact, if we look at this chart provided by NASA and Penn State, we see that the Earth has not had our present level of carbon dioxide since 2.5 million years ago. On the other hand, carbon dioxide exceeded 1,000 parts per million as recently as 30 million years ago, when primates had appeared. Bear in mind that mammals have been around for 300 million years. One way of viewing this chart is as a record of the depletion or even starvation of carbon dioxide as it became sequestered in limestone, fossil fuels, land plants and the ocean. This coincided with cooling, which culminated in the repeated ice ages starting 2.5 million years ago. So our ancestors as far back as Homo erectus have only known this cooler period. It seems likely that we could reach a level of 600 parts per million by the end of the century, provided we do not run out of fossil fuels before then. In itself, this is not a problem. We breathe out 40,000 parts per million, and we regularly come across levels of 600 parts per million in forests and auditoria, not to mention our own homes. We in New Zealand are very aware of El Niño and La Niña and the profound influence these have on our weather. At the other side of the Pacific, the United States is also affected by these influences. Essentially, El Niño describes the event when warm water appears in the eastern Pacific, with cooler water in the west close to Australia. La Niña describes the opposite conditions. Typically this happens at irregular intervals of 2 to 7 years and has quite profound effects on temperatures and rainfall. The chart, which shows the view from the United States, demonstrates the sporadic nature of the events, seemingly unaffected by CO2 emissions. A longer-term effect on weather is provided by the Pacific Decadal Oscillation, which occurs above 20 degrees north. There appears to be a marked correlation with known temperature phases in the United States. That is, warm in the 1930s, followed by cooling to the 1970s, warming to 1998 and cooling thereafter. The Atlantic has its own multi-decadal oscillation. It is not doubted that Arctic sea ice is affected by this. These ocean oscillations serve to remind us that the world climate is complex and not driven solely by carbon dioxide. Sunspot observation goes back to Chinese astronomers around 800 BC. The earliest known drawing of sunspots appears in John of Worcester's chronicle recorded in 1128. There has been an enduring belief that sunspots influence weather. Sunspot activity is related to the sun's magnetic field. When the field is strong, there are large emissions of solar material, and these are visible as sunspots. When the magnetic field is weak, the sunspots diminish in number. Sunspot activity rises and falls with an approximate 11-year cycle. When the magnetic field is strong, the planets are protected from cosmic rays emanating from the galaxy. When the field is weak, cosmic rays strike the Earth and increase the rate of cloud formation, thus causing cooling. That is the theory. The magnitude of the 11-year cycle varies over approximately 400 years. Dr. Valentina Zarkova of the University of Northumbria has fitted a mathematical curve to sunspot data. Notice the period around 1600 when sunspot activity was low. This is known as the Maunder minimum after an observer at that time, and coincided with the start of the Little Ice Age. Also notice that according to this chart, another solar minimum is imminent. This gives rise to speculation that we may be heading into a new mini-ice age. The link between cosmic rays and cloud formation has been proposed by Henrik Svensmark, a physicist and professor in the Division of Solar System Physics at the Danish National Space Institute in Copenhagen. According to Svensmark, around 50% of recent global temperature rises can be attributed to solar activity. The current lessening of solar activity could explain why temperatures since 1998 have not been rising significantly, while CO2 has continued to rise. This chart shows how cosmic rays increase when sunspots are low and vice versa. A second chart shows how cosmic rays are related to low cloud cover. A third chart shows the relationship between tropical cloud cover and temperatures. Research is continuing in this area, but at the very least the theory does call into question the IPCC contention that all recent warming has been caused by CO2 emissions. Discussion of climate would be incomplete without mention of the Milankovitch cycles. In the 1920s, Serbian astronomer Milankovitch hypothesized that variations in eccentricity, axial tilt and precession in the Earth's orbit influence climate. Eccentricity describes the varying elliptical orbit of the Earth and has a cycle of around 100,000 years. Axial tilt has a cycle of around 41,000 years. Precession, or wobbling like a spinning top, has a cycle around 26,000 years. These cycles are too long to influence climate over a millennium, but they can be used to explain the recurring ice ages. That concludes the third part of the series. In the fourth part we will be speculating as to what the future holds.